Hi everyone, welcome to the session. I'm Mallory McLemore. I'm CEO of Stell Engineering. I'm so excited to be back here at an AIAA event. I attended my first AIAA conference as an aerospace engineering student 10 years ago this year. I'm excited to represent Stell Engineering. We have raised millions of dollars and we've been working for years to replace outdated, difficult requirements management tools that I used as an aerospace engineer. So excited to welcome our panelists. Thank you for sharing your perspectives today, and thanks to AIAA for hosting. Enjoy.
Good afternoon. Welcome to the Forum 360 that is advancing digital engineering with pattern-based MBSE. One of the areas that we've all heard a lot about is digital engineering topics, whether it be digital threads, digital twins, the words go on. And a lot of what is out there, what we need. But how are we going to unify many different digital threads? How are we going to unify the information that exists between a lot of different organizations? How are you going to have information be consistent? And that's where patterns yield a lot of promise. Pattern-based MBSE, specifically, is a way that we can enable the advancement of the digital engineering promise. Let me see. So we have 6 panelists that are going to help us understand this landscape. We have our first speaker is Bill Schindel from ICT System Sciences. He's the president of ICT. Speaker number 2 is Dr. Olivia Fisher from Georgia Institute of Technology. She's the Chief Digital Engineering Division. Speaker number 3 is Dr. Jimmy McGever. He's from Johns Hopkins University Applied Physics Lab, principal scientist there. Fourth speaker is Dr. Danny Selva. He's an associate professor in aerospace engineering at Texas A&M. Fifth speaker is Dr. Marilee Wheaton. She's a fellow out of Aerospace Corps. And finally, we have Dr. Tom McDermott, who is Deputy Director and CTO of CERC. So with this panelist, we're going to give you a broad perspective of a lot of different topics and how could you unify them. They're going to seem very different. A lot of what we're going to be talking about is coming from, or it's already been published in, several articles. These are some articles outside of AIAA through INCOSE. We're leveraging a lot of learning and a lot of knowledge that has come through INCOSE for the past several decades. We're just making it more aerospace specific. But there's a lot of learning that we can use from other industries, such as pharmacy, medical devices. The list goes on, transportation, that have already learned, and this is a validated methodology that has been used that we think has promise here. So these are written about inside a lot of INCOSE publications. To make them more relevant to this audience, you probably have seen these articles. If you haven't, I encourage you to download them. The first one is the digital thread. Well, to my left, to the left over here is digital thread. And that one gets into what is it and why should I care? The other one is a digital twin implementation paper. It's a lengthy paper and it goes through 8 different digital twins that are real, that exist, they're not notional. And how can we unify the information between these very different digital twins? Some are space, some are aerospace, some are buildings. There's a lot of different types of information there. So how can we go through that? And finally, when we look at MBSE, which holds a lot of foundational knowledge and capability that we're going to leverage. This is out of the 2023 NDAA, where MBSE is now being used across the board for DoD for transparency and coordination. It's now what should have been a lot of people have been using. So this is a step in the right direction, but it's not going to get us to information consistency by itself. We're living in a realm where a lot of models, even system models, are inconsistent within a single program. Style guides won't do it. Different frameworks aren't going to do it. You end up with models inconsistent across an enterprise. So, how can we make these models consistent? How can we have information be consistent between different types of models, different organizations? That's where we believe that advancing digital engineering through pattern-based MBSE is the way to go. And the last bullet on this is kind of the emphasis of this. MBSE itself can be consistent, but as it's practiced, it is not. And that's because a lot of people are not utilizing a framework that would allow for completeness and allow for the same kind of information to be in there. And that's where patterns come in. Pattern-based MBSE allows for a lot of that, and we're going to start talking through it. So you're going to hear from the panel today about different topics. You're going to hear from autonomy. You're going to hear about dynamic requirements. You're going to hear about different capabilities or challenges that need to be out there. And solving one is great. Solving them all would be fantastic, but how are you going to unify all that information across different organizations? That's where the patterns comes in. So with that, I encourage you to ask questions on the app. Be looking for them. And we're going to start off with our first speaker is Bill Schindel from ICTT. There you go, Bill. That's advance. Backwards. Big green to advance.
Okay, thanks. Thank you, Matt. Welcome, everyone. I'm Bill Schindel. I chair a working group in the System Engineering Society in INCOSE called the MBSE Patterns Working Group. And some of what you'll hear here represents that point of view. Since the name of that working group is the MBSE Patterns Working Group, it seems to be about models and patterns, people sometimes think that when we talk about patterns, we should think about maybe templates or something like that we use over and over again in our models. And I guess one of my early messages to you here today is you're shorting yourself if you think about it that way. Patterns are much, much more than some kind of information artifice for making models, even though they do that very well. Patterns are the basis of most of what we all do and think about. They're regularities in the world. They're things that we observe that are recurrences that occur across time or space or different projects or different product lines or different situations. They're the basis of whatever your discipline might be in maybe engineering or aerospace, behind it with the edifice of STEM, science and engineering and mathematics. It's all entirely based on patterns of particularly the last, let's say, 300 years since at least Newton, give or take, the basis of all those disciplines. Patterns are the basis of the theoretical foundations of the physics and other disciplines that support what we do in aerospace. Patterns are the basis of learning, as we are all trying to do here today, or if we're a learning machine, Patterns are what AI machines learn. Maybe we don't say that so often. We treat them as some kind of black box, but what they're learning are patterns. Patterns are the basis of cognition and reasoning. So that's the way to think about patterns. And yes, we happen to be using them in model-based system engineering to represent some of those things. But you should think about them as something more broad than just a modeling technique. Maybe from the more negative point of view, patterns are the things that we didn't learn when we make mistakes over and over again, or when we miss opportunities repeatedly that we wish we'd learned sooner. Patterns are what make the world recognizable most of the time, or maybe not so recognizable sometimes. Patterns always turn out to be, when you get formal about them, they're partly fixed. They have aspects of them that are invariant, and they have aspects of them that are variable, that are parameterized. They're described informally in natural language. You can talk about patterns to your family or to elementary school children. Patterns were practiced with great success by civil engineer Christopher Alexander in the form of prose templates. So they're not always so highly formal, but in what we do in the MBSE Patterns Working Group, our patterns are formal descriptions in the form of models. And just like what happened in the STEM revolution, that's when patterns got really powerful, is when we could combine them with the power of mathematics and other data structures. So when they're described formally, they're described in the language of math and science and engineering and mathematics. They're not just patterns about engineered products. You might think, as aerospace folks, we might think about patterns that describe our aerospace products, aircraft, patterns of fluid dynamics and wing surfaces and otherwise. And that's fine. A lot of what we do in INCOSE is concerned with patterns of engineered products. But patterns also describe the system of engineering and production and sustainment that we have. What we're really mostly talking about in these meetings is how we do things. Those are patterns too, and those are systems that are representable in this way, and they're some of the most interesting patterns of all. So in our working group, we've been very interested for the last, we're a 10-year-old working group in representing patterns of engineered products, but especially the patterns of doing engineering and production sustainment and otherwise. And you'll see that, I think, from some of the other speakers. In our working group, a subset of those patterns are concerned with what we call the smallest model necessary for purposes of engineering and science. If you think about all the different kinds of models you could have, what would be the smallest model content that would be sufficient over the life cycle of an engineered product to describe it for purposes of engineering or science? So that's something we would claim we have some understanding of for the last few centuries, at least, of engineering and science. So we ought to be able to answer that. And the answer to that is based on an underlying framework, an ontology, if you like, or a meta-model called the Systematica meta-model that we make use of, or S-star meta-model. And so that's a subset of all the models and patterns we could describe that's sufficient to have the content to cover that space, that ontology. And if you're interested in that, you can read more about it from the references. It describes the elements and the relationships between them that would be sufficient for purposes of engineering and science in different situations, not discipline specific, but before we get to individual disciplines. That ontology's been mapped to a lot of modeling tools, so it's a neutral thing that we make public through INCOSE, so it's not proprietary in some particular way, given its purpose. And then we're concerned with patterns, S-star patterns, Systematica patterns, that are models of generic families of systems, whether they're engineered products or how we do our work or otherwise. And when we practice with those, we don't have to create models from scratch every time. We're constantly referring to existing patterns that exist and configuring them, often by automatic means, into a specific model that we know by construction has some extra confidence in it because of what it goes through to become a trusted pattern. And those things are called S-star patterns because they're S-star models that are configurable and reusable, and they satisfy the S-star meta-model. All things that you can read about if you're interested in the references. The patterns we're interested in our working group are primarily what you might think of as big system patterns. So they're They're not just design patterns for a part or how we make a hinge or a motor or something like that. They're typically, because we're a system engineering society, an entire product line, an entire platform system. No reason why you can't model something smaller with them, but typically the ones we're doing are larger. But we also model, as I mentioned, how we do engineering, how we do production and sustainment. And so that pattern, it is also a pattern, is called the INCOSE Agile System Engineering Lifecycle Management Pattern, the ASE-LCM. And you'll see it appear sometimes in some of the material from the other speakers, because as Matt told you just now, we used it as the basis for the AIAA reference model for digital threads and the AIAA reference model for digital twins. And those are descriptions of how we do things. The ecosystems, it's sometimes called the innovation ecosystem pattern. So that might be of interest to you as well, and there's a picture version of it if you're interested. So this last slide shows on the right side a simplified block diagram that represents the underlying model. If you're into it, you can open it up in SysML, but it's a description of what does it mean to be an innovation ecosystem? What does it mean to say that we're describing things with models and we're learning things from feedback and we're incorporating that learning into patterns that weren't quite right but get better all the time? What does it mean to say that we deploy those patterns as models and how we manage their trust and how we do in V&V of them? Generally what it means to be an innovation ecosystem. It's a pattern in its own right, and we use it for lots of references. And underneath it is the S-star meta model. Or you could think of it as a common core ontology that describes systems of all sorts, whether they're molecules or aircraft carriers. And those are things that our working groups are engaged in. We do lots of things with the AIAA, as we've said. So you're invited to not only be part of our working group, but as AIAA, interact with us as well. We'll meet again as a working group in Sevilla, Spain, in just a few weeks. If you're interested in any of this, please don't hesitate to contact me. Thank you.
Thank you, Bill. Next, we're going to hear from Dr. Fisher, who's also the chair of the Digital Engineering Integration Committee, and about the products that have come out of there, the promise of digital engineering. What are those topics about? She's been spearheading a lot of these efforts within AIAA, within Georgia Tech, and elsewhere. So turn it over to Olivia.
Thank you, Matt. All right, good afternoon, everyone. It's my pleasure to be here again with you. So what I wanted to speak about is a little bit of the context in which we believe we can all benefit from the use of pattern-based MBSE. And so just for context, we're basically developing assets that are in capability, that are rapidly increasing in complexity and operate in an environment that are highly contested and also very dynamic in nature. And so to maintain operational superiority, it is really important, and more than important than ever, that we're able to bring data-driven decision-making capability up to the mission engineering and operator level. And this capability is really only possible if we have some level of digital continuity and traceability from requirements to design, to manufacturing, to test and evaluation, all the way to operations, sustainment, and missions. And so when we talk about digital continuum, what we really mean is this ability, this way to exchange data, model, and information throughout the dimension of the product or the system lifecycle, but also the V&V, verification and validation. So going from system requirement to mission engineering, but also from system component all the way to mission outcomes. And so if we look at the product lifecycle more specifically, throughout the life cycle, we have many opportunities to exchange data, models within the same organization, but also across organizations. And what that means is that there's a lot of ways for inconsistency to arise. And so you can have inconsistencies between product process specification, for example, and part design specification. You can have inconsistencies between program schedule and priorities versus acquisition status and the like. And so obviously those inconsistencies need to be identified, they need to be resolved, And the later you do that, the more expensive it is, the more time it takes. So the question that we're asking ourselves in this effort we have ongoing with Northrop right now is how do we address this issue through the implementation of consistency threads and MBSE pattern. And so very briefly, for all intended purposes, what we're currently doing is leveraging the Northrop Grumman MENAO model. And this model has been actually previously used to look at the link between design and manufacturing. So what we're currently investigating within our research project that started pretty recently is how can we use this model to identify the kind of predefined interaction and minimum set of information that are necessary to model operational and sustainment framework, and understanding how robust that pattern is going to be across different operational and logistic scenarios. And so if we're successful in this endeavor, we hope that the application of pattern-based MBSE is going to help us better understand eventually how design impacts higher level mission and operational capability, but also how changes in mission requirements or desired mission outcomes are going to inform maintenance and resupply needs in terms of part, equipment, and the like. Thank you.
Thank you, Dr. Fisher. Next, we'll hear from Dr. McEver about dynamic requirements.
Thanks, Matt. I want to shift gears a little bit and talk somewhat about the sort of the nature of the problem that drives us to need to think about these things in slightly different ways. This is an activity that came out of a task force that AIAA stood up over the course of the last year and a half, to focus on the idea of how do we need to transform our systems engineering approaches, our systems engineering environments, not just digital engineering, but more broadly than that, to deal with a lot of the challenges that we find in our operational and technology spaces. I've been involved in one of the working group that has specifically been looking at this question of how do we better deal with dynamic mission requirements? What do we do when the environments that our systems are deployed in, that are the problems that our systems need to address, begin to vary from what we had on the drawing board when we built and designed those systems. So we really seek to understand how do those kinds of changes manifest and what kind of challenges they pose both for the systems as well as for our engineering and design activities. Ultimately, what we're trying to get to is this notion of, all right, well now how do we need to evolve our engineering ecosystems and our engineering approaches to better deal with these kinds of things. I think that there is a sense in which if we are trying to deal with change in the environment, first off, what we want to do is to really try to understand, well, what is the nature of that change? What are the sources of that change? And rather than dealing with each instance of that as sort of its own unique case, we tried to identify different classes of change sources, different classes of sources of dynamics. And I won't go through all of these in detail, but the purpose of trying to identify these different sources is both to help us be comprehensive when we're in the design phase of systems, to better ask ourselves, all right, what kind of change could we or might we expect that system to face in its operational use, but to also try to understand, well, do different sources of change, do they put different stresses on our systems and on our engineering processes? Both in the sense of, do we need to respond to those changes differently, but also do we need to alert ourselves or sensitize ourselves to detect those changes in different ways. Likewise, there are different ways in which the needs of our systems are going to evolve, right? It might be that we've got some change in capacity or some new functionality that's needed, or some new robustness or resilience is needed. You can think of this from cases as simple as, oh, well, the temperature environment now is going to be slightly different than what we designed for. Or you can think about it as, okay, well, I've got a swarm of UAVs that are now going to conduct a search and rescue mission when they were designed to conduct a strike mission or a surveillance mission. How do we prepare our systems to be able to deal with those? In addition, there are a lot of different factors that impact the options that you have as you respond to these. Where that change happens when you're in the life cycle. Is the system still on the drawing board, or is it all deployed and out in the field? Is the change that's needed something that's doable in software, or would it require some sort of hardware configuration? I think the information component of this is really important, right? How do you become aware of that change? How do you become aware of the need now that your system has to do something different? That involves a very strong decision-making and command and control component, which in the area I work in, which is cyberspace operations, we see a lot. I mean, we deal with change and the emergence of new challenges all the time. And I think this is one of these areas in which pattern-based systems engineering can be a real boon to help us sort of have some different mechanisms to deal with change in our pockets ready to go and pre-built into systems. And I think Tom is going to talk about an instance of that a little bit later. I want to be specific that when we talk about responding to change, I think that we can think about that at different levels, right? We can both think of changes that, things that the system is going to have to do differently, but I think we can also think about things that we have to do differently in our engineering processes. There's a really interesting paper from Haberfelder and DeVeck from a few years ago. Well, I guess it's 20 years ago now. It seems hard to believe it's that old, but where they differentiate between agility and our systems engineering processes in questions of how do we engineer agility into our systems. And I think while there are some commonalities in terms of the context, these are two really different use cases that it's worth thinking about how we approach this. I'll make reference a little later to the fact that I think that this is a really recursive problem that even some of the patterns that we apply in our system, in our engineering of systems, we can also begin to apply to how we engineer our engineering approaches and how we design our enterprises to better deal with these things as they cascade. I think a couple of examples of some things that have emerged in the literature that may sort of form the basis for patterns are going to be concepts like development margin and operational margin. These are ideas that we use over and over in engineering management to help us deal with the change that we routinely see during our design activities. Likewise, there are some concepts or core aspects associated with agile systems engineering that can also serve as sort of patterns for this. Things like product line architectures and methods of continuous integration and testing. Again, I won't go through all these, but I think that ideas like this can serve as foundations for the construct of patterns that we can then begin to apply in our systems design and in our engineering approaches. And lastly, I'll just sort of return to this idea that really change impacts us at all these different levels. A lot of times when we think about dynamic mission requirements, we think about what does a system have to do differently. But as we recognize that our systems are going to routinely be in dynamic mission environments, I think that propagates the need for change back through engineering processes, back through even innovation processes. And so you can sort of think about, where does that change occur? Well, those dynamics can be stresses on the system, that can be stresses on the engineering life cycle, but they can also be stresses on our enterprise. I think that's another way that patterns can come into play here, and that is that they can help us think about these things not as three different, distinct, unique problems, but as different aspects of one connected problem. Thanks.
Thank you, Dr. McEver. Next, we'll hear from Dr. Selva talking about autonomy.
We've all educated.
Forward is the green button.
Colorblind, so is it this one?
This is forward.
Thanks. Good afternoon, everyone. I'm Danny Selva. I'm an associate professor at Texas A&M. I'm excited to be here to talk about patterns, which is not only a beautiful concept, as you could see in Bill's presentation, an elegant concept, but also something that has, I think, tremendous practical importance in systems engineering. All right, so I want to acknowledge, first of all, the contributions of Mitch Ingham from JPL to this slide set. Mitch, unfortunately, could not be part of this panel, so I had to replace him kind of last minute. These all started also in this transformative engineering of systems task force. You just heard about it from Jimmy. So one of the other working groups that I was a part of was working on the idea of autonomy, and specifically looking at autonomy as an application area for, or as a driver even, of transformation in the systems engineering process. I think it's not hard to understand or imagine that autonomous missions, and I'm a space guy, so I will give you a space example. We are going to go to deep space planetary bodies like Europa, ocean moons and so forth, where we have very little information about those places compared to, say, the moon and Mars. Long communication delays, which makes controlling those missions much more challenging than in cislunar space. And that's all just going to drive the need for much higher autonomy, right? Including, of course, dynamic requirements, right? Making a connection to what Jimmy presented. One of the Sorry about that. You could imagine that this mission that would go to Europa, rover on Europa, would be an excellent example of some of those dynamic requirements. Scientists may not even know what their priorities are going to be until we get there and we can make some measurements and get some observations on the field. Either way, a key point in autonomy is that autonomy needs to be architected, and this is something that I wanted to make that connection between the pattern-based side of things, but also system architecture and autonomy. So we don't want autonomy to be an afterthought, something that's added on after the fact. We want autonomy to be architected since the beginning. And that's how pattern-based systems engineering practices can really help autonomy. I'm going to go very quickly through this, but just to give you all the information, we've done a couple of workshops at both Ascend and Aviation to try to understand in more detail how autonomy is going to drive this change in systems engineering practices. So we actually focused on breaking down what autonomy means in terms of different use cases and different metrics. So different use cases will have different concerns, different needs, and different metrics. So documenting all of that. And I'm not going to go through all of these, but just to give you a sense of what those look like, this is the outcome of the Ascend workshop, looking at the space use cases. So you can see a bunch of different use cases here. One of the ones this is Mitch's favorite, is the long-range lunar traverse. So we're not talking here about moving, a couple of centimeters at a time on the lunar surface. We're talking about being autonomous for long periods of time. That brings some challenges. Autonomous sensor webs is something that's very near and dear to my heart. That brings other concepts of, completely dynamic networks, topologies, sensors of different characteristics coming in and out of these networks. We did the same thing at Aviation with autonomy. A bunch of different use cases came up, such as a loyal wingman or some kind of digital assistant for the flight deck. Of course, the question at hand here is how can pattern-based MBSE help with autonomy? And some of this is, pretty general across all domain areas. More consistency, more integration across different disciplines, across different organizations. And eventually for autonomy, that means trustworthy autonomy, which is one of the hot topics right now in the world of aerospace autonomy. Just to give you a couple of examples to close out in terms of how pattern-based MBSE has actually already been applied to autonomy. You have here an example out of JPL, which is this goal-based control architecture pattern. In case you are not aware of the way that we control spacecraft, typically it's based on time-based commands. So you just send a sequence of commands with a time tag associated to it. As you can imagine, that's not very robust. And as the level of uncertainty increases, when we go to these new places, long communication delays, we need something that is going to be more robust than that. So a goal-based control architecture is an example of a solution. Remember, the pattern has a problem side to it, a recurring problem. It could appear across different domains of applications. And then there's a solution to it. And here you see the solution in terms of some models, right? So this is based on architecture description language. You can see here some of the detail, but you can also do it in UML, SysML. And eventually, of course, the hope is that this can tie directly into reusing code, right? The hope with patterns is eventually to reduce cost and risk, right? So being able to reuse code is one of the holy grails. And I'm going to end with something a little bit different. You've seen patterns as essentially reusing SysML models. I'm exaggerating a little bit, right? But essentially reusing pieces of a solution. But you can also apply ideas of patterns to more the process side of things. How do you make decisions? How do you make system architecture decisions? There's also patterns that can be identified in terms of the kinds of decisions that we have to make. This is some work that I did with some of my students in terms of identifying a series of patterns about assigning, combining elements, partitioning elements into subsets. And we tried to provide, on the part of the solution, both quantitative and qualitative guidance, right? At the end, patterns are all about reusing knowledge. I'm going to stop there.
Thank you, Dr. Selva. The next speaker will be Dr. Wheaton from the Aerospace Corps, talking about where contract seed rules are going.
That one is next, okay, thanks. I think my topic may be the likely most pragmatic application of MBSE patterns, but I think it's really important because if you really on development programs in the government, if we want to get consistent models and models that meet our needs, then the use of MBSE patterns is really important because not just for an individual program, but as mentioned before, when you try to integrate things across an enterprise, right, you want that consistency and you want those patterns. And so to that end, Aerospace has been supporting Space Systems Command, the Space Systems Integration Office, SSIO, in Los Angeles, and we've been working on digital engineering contract language for them because it's currently, if you look at the guidance for contracting language and for the data item descriptions, there really isn't a lot out there. So one of the tasks that we've been doing for them is working on that. And so it's kind of work in progress now, but there are some artifacts that actually are available now that can be used. So, we really feel like to date, we didn't have things that supported a clear definition of expectations related to digital engineering. As Ms. Baldwin mentioned this morning, there's policy now in DoD 5000.97 that really talks for acquisition programs, the things that are needed for digital engineering. And one of the key areas they talk about is related to what we put in our contracts and our RFPs and the data item descriptions that we use for the contract deliverables. So we do have some current activity efforts that are going on. They fall in the areas of style guides. SSC has a style guide that was just published. They have been working on a government reference architecture as well. And then the things that we have been supporting them on are this system architecture model DID, which I'll be talking a little bit more on our panel on Thursday, where we're going to delve into digital system models. And actually, there is already a DID for a model development plan that's based on some work that Aerospace has done that's actually in the ASSIST database that can be used. And so, as I said, we're working on an update to the SAM DID. We have the model development plan, and then we've been doing a lot of training related to those areas. And so the idea is, can we support better digital engineering wording in our acquisition documentation? We're also working on a technical operating report that is actually out, but now is going to be turned into an SSC guidance document that's going to help the programs with identifying RFP statements that they can tailor and then use on contracts when they ask for models to be delivered on those contracts. So, the goal is achieving standardization. So, we'd like to have standardized statements of work guidance available. It's not compliance document, it's really more guidance because, as you all know, we have to really tailor them to the need. But we did this work not just from our aerospace experts, but the government, and then we put it out for industry review and got a lot of feedback from industry because it's really not helpful to put something out there and then after the fact of industry come back and say this is, not workable or there's, unintended consequences. So we've kind of gone through a rigorous process to doing that. And so our current effort is focusing on an update to the statement of work, RFP statements for systems, for digital engineering. And then also we have these 2 data item descriptions we've been working on. The digital twin one is actually ready to go into ASSIST. It's kind of already gone through the process, and SSC will be submitting it to ASSIST, and that process actually takes several months because they have to go through their process. But we're really excited about the fact that there would be a data item description that will explain the delivery requirements for a digital twin, not the requirements for what it should be, which would of course be vary by program, but the delivery requirements. And then the system architecture model. And the system architecture model is the one that we specifically use the MBSE patterns work on from the INCOSE working group. So we use that framework as we were developing that more extensive system architecture model did. So that's the tie-in there with the work being done here. And then, it's really kind of evolving. The SSC goes through a lot of planning increments, or using an agile process to do that. And as we learn more, we're updating the documents. So there's plenty of work going on, and we'll keep improving these artifacts related to DE-enabled acquisitions. And so the ones that are currently out there is, this is the aerospace tour for RFP statements. It's got a distro C, which is all government and DoD contractors, which really is pretty broad. And then we have the draft digital item description did. That tour is also distro C, but it's going to be turned into obviously distro A because all of the DIDs that are in ASSIST are available for public release. And then, as I said, the one we're still working that's just coming out is the system architecture model data item description. But if anyone is interested in any of these, they can contact me and I can get them to you. And the use of them are really to be tailored for certain acquisition needs. And types of use cases, you could use them for concept of operations, use them for deliverables. A lot of the models that are being developed are for reference architectures for systems, either at a program or an enterprise level. And again, there you would, by using the MBSE patterns framework, you're going to have consistency across those models are going to be developed. You can use them to identify stakeholders and users of deliverables, and also for training as well. So we've been doing a lot of training related to digital engineering and on the use of deliverables. So they have a lot of uses, and we really believe that this work is really going to contribute to the consistency and the success of the programs, not just for SSC, but DoD-wide. Thanks.
Thank you, Dr. Wheaton. Before we get on to our last speaker with Dr. McDermott, reminder, we get your questions through the app. So I'll be looking at those after we finish up with Dr. McDermott. There you go. Button advances there.
Great, thank you. Last week I was at Navarre Beach, Florida, which is a barrier island on the Gulf Coast near Pensacola. And one thing you'll notice about this particular beach is every building is on stilts, 15 feet off the ground. Every building that wasn't got wiped off the island in Hurricane Ivan in 2006. And so this idea of putting buildings up on stilts is a resilience pattern that gets followed pretty religiously and encoded now. And in fact, you can download Army Corps of Engineers document that describes how you should build buildings in coastal flood zones to do these patterns. So resilience is an area where pattern-based design is just essential because the context and the system are always interacting, and they're always changing. And so explicit designs have to be replaced with patterns. And so when Christopher Alexander published the patterns book on building architecture a long, long time ago, the idea here is that we can see these patterns and then we can reuse them and turn them into best practices. And so building architecture really focused on physical patterns, and it's really focused on patterns that drive the utility of the physical spaces that we operate in. When we go into software or system engineering and we start talking about things like resilience, we can't see it, right? It's invisible to us, it's encoded, it's purely based on behaviors or functions in the system, not on physical constructs or the utility of those. And so resilience really requires pattern-based engineering in engineered systems, in software, in systems engineering. And the engineers that work on these systems and want to design in resilience, they need lower level definitions of resilience controls and functions. So patterns in MBSE are useful tools. And the goal here is we want to design these things in. So we've been doing this work in cyber resilience. How do you build cyber resilience or systems that are resilient to cyber attacks, which means they detect them and then they recover from them without losing the mission or with safely exiting the mission, or however you want to do that kind of thing. And so this is something that can't be added onto a system. It's very difficult to take a building and put it on stilts 15 feet in the air after it's already been built, right? You got to kind of plan for that up front. It costs money. I don't know, how many of you have experience with putting buildings on stilts? $30,000 to $100,000 is the cost to put a building on stilts, and it's very expensive to do these resilience patterns, and they all have costs. And so we need to do the designs up front, and we need to do the design trades. So in the cyber resilience, we have this meta pattern that we've been promoting called a Sentinel. This was thought up by Dr. Barry Horowitz when he was at University of Virginia. And the idea here is that there has to be a behavior or a function in your system that monitors for behavioral abnormalities that are signals that you're being a cyber attacked, or it could just be failures if you wanted to call it that. And when those things are detected, it invokes a new function that's designed to recover the system in whatever form it needs to be recovered in. And so this thing called the Sentinel pattern, it's sort of, we call it a meta pattern because it derives a whole lot of patterns underneath it. In the work that we've been doing in cyber resilience, the whole concept here is how can we do this in a model-based environment so we can do engineering trades? Because it costs money. Where do you need to have the functions? How do you design what's the highest priority threats? What's the highest, most critical functions that need to be protected in these systems? And then how do you measure that in the test environment? Because you can't see it. If you can't test it and invoke it, then you don't know if it's ever going to work, right? So this cyber resilience meta pattern is one of those things that then makes this very concrete. And in all of resilience engineering, we need to have these types of things. So MBSE turns out to be really useful because we can encode these generic patterns as functions in system models. So in the picture here, there's this thing called a resilience pattern, which is one block in an overall model of the system. It's a class of function that the system can invoke in order to counter a cyber threat. And then underneath that resilience pattern, there's a number of different patterns that correspond to a handful, maybe 30 traditional resilience mechanisms that you would put into robust computing systems. So none of this stuff is really new, but it's not stuff that has to be looked for. So the idea here in our future is that MBSE is going to be quite a useful tool to capture knowledge. We've now got a project started up to do the same thing, looking at resilience of AI systems, not so much because of the external threats, but some of their behaviors are unpredictable. So they have some of the same behavioral effects that cyber attacks have on systems. So call, MBSE. Great. So I'm going to start off and maybe ask the first question. So Christopher Alexander published the patterns book in architecture. It changed the nature of how we do architecture. The Gang of Four published the book on design patterns in software. It changed the nature of how we do software development, or software reuse at least, in some of those environments. The question is, as we get to patterns in system engineering, how are we going to distribute that knowledge, and how are we going to get people to adopt it? Sit down and let y'all answer it.
Thank you. So we had agreed that that was going to be the first question, get people calibrated to our panelists and to the app and upvote things. That was one of the questions, actually. So go ahead, Marilee.
I'll start, because I think that question is directly related to what I talked about, which is when we do our contracting for programs, we need to ensure that we clearly state both in terms of our RFP, what we're looking for. If we're having models delivered, we need to ensure that they have that consistency. If we'd like them to use or consider using a certain framework, we need to identify that. So I do think we have to have clear RFP statements. We have to have clear instructions. And when we think about the deliverables that are coming in, to ensure that the DIDs reflect that. And I think the ones that are currently out there insist we're really very oriented toward paper products, right? So there aren't really a lot that are toward the digital transformation that they were hoping. So that's why I think infusing some of these, both in terms of guidance for RFPs and DIDs that actually then support digital transformation, and having artifacts provided such as MBSE models can help with that adoption.
Thank you. Go ahead, Jimmy.
So I think that there are a number of considerations. There are a lot of different levels that you can think about that question at, right? I mean, so one has to do with the things that merely you were just talking about. Are there standards for the expression of these things so that they can be used in different ecosystems and by different tools and that sort of thing? I think there also is sort of this tension between the sharing of patterns and the fact that the patterns might represent, sort of the secret sauce or the intellectual property, something that is unique that a particular innovator has brought to a problem. So I think it's important to understand, is a standard sort of in the commons generalized approach that you want to take, because it's important that these processes represented in this system be consistent with and interoperable with some other systems they might need to interoperate with, or if it actually is something that represents the innovation that a company is bringing. So I think that there's no necessarily a sharp line there. I think it's just something to think about. Regarding that, though, the other question that comes in has to do with sort of the information security question, right? So if you're expressing important design considerations, if you're expressing important processes, best practices, these kinds of things in patterns, how do you ensure that those patterns are both available to those it should be available to and not available to those that it should not be available to? We had this big discussion in a workshop here on Sunday about sort of this question of, well, now when you introduce the fact that we're doing our engineering not just for a cyber contested environment, but in a cyber contested environment. Now, we've digitized the things that adversaries might and competitors might particularly place great value on. So this becomes another consideration that we have to think about. So like I say, there are a lot of different levels. I don't know that there's necessarily an easy cut and dried answer to it, but it's a really important question, because in order for these patterns to be valuable, we have to have answers to these things.
Anybody else?
Yeah, sure. I think for us, it's being in education, right? It's getting the students to understand that pattern-based MBSE share the same kind of foundation and principles than MBSE. And so for all the benefits that were highlighted in this panel, this is important for them to become familiar with the concepts, the principles, and develop use cases and opportunities for them to apply those principles. So that's kind of what we're trying to do through collaboration with industry, make sure that the use cases that we're leveraging to teach those concepts are obviously relevant and addresses bigger problems, but at the end of the day, we're not just teaching MBSE for the sake of doing MBSE. It's like, what is the higher purpose of this?
Well, and I think that for a lot of new problems, I'm glad that you brought up the student and the educational aspect of this, right? A lot of times when it comes to new problems, we do a lot of reasoning by analogy. We'll say, well, look, this is how the command and control community addresses this thing, so now we'll map this over here. And it's always a question of, well, how good is your analogy? Where does your analogy break down? With pattern-based systems engineering, you now have an opportunity to formalize and test that analogy. And understand, what it actually means to map a pattern from one domain to another, and can answer that question about, well, where does it break down and under what conditions is it valid? And I think in particular, using that, making sure that students are armed with this is going to be it's potentially a very transformative thing for the next generation of engineers to have at their fingertips.
In addition to the education and training, which is important, not just at the university level, which clearly it needs to start there, but also in industry, because you've got some upskilling that needs to go on between industry and government. But I also think there's this cultural aspect of sharing, because one thing we're finding is, even if we've got, let's say, patterns out there or guidance recommendations, just having people having that culture of sharing, where when you're trying to bring stuff together and integrate it. So I don't think we're quite there yet. I think to be successful in digital transformation, you have to have that culture of sharing and realizing that, yes, from a cyber perspective, there is going to be some protection there, but also just that it's okay to share what you're doing and have it be integrated into the whole. So that's, I think, a key aspect.
I'll let Bill finish this question out and get ready for the next one here in a second.
I think it helps to ask ourselves, what outcomes are we trying to encourage with patterns, because otherwise it's just a way of doing things. And we should recognize there are disincentives as well as incentives to using pattern-based methods. So a couple of examples on our working group is the patterns we generate. I told you about these S-star patterns are such that they are rapidly, through automation, capable of generating models. And what that means is that we can invest in a pattern that's a formalization and generate many, many models from it by automated means that are highly trustable. Now, if that's not an outcome you want, then it's maybe not an incentive, but the effect of it is that many more people end up using and producing models, but many less people end up actually generating the underlying model because of the auto configurability driven by what some local user is trying to do. So you have to kind of look at the system level view of the ecosystem and say, what are we trying to accomplish here? Another security related thing that's interesting is that because patterns of the type we're talking about have fixed and variable aspects, if you take a general pattern and generate a configuration of a specific aircraft, and then separate the configurable part from the fixed part, you have an encoding that's a secure encoding. And so by separating the two from each other, it's a helpful thing if you're trying to be more cyber secure.
Great. That was a good question, good start-off question. I appreciate you asking. It was very similar to a question that's rising in the upticks of how do we distribute these MBSE-based patterns and get people to use them. The one that is getting the most upvotes right now is what current aerospace projects have benefited most from pattern-based MBSE. And can you share examples from this approach? And if you know of some, share them. You can share, and maybe some other examples. Like I said, out of AIAA's publication, there's 8 digital twins published in there with pattern-based methodology unifying them all. But maybe for patterns in aerospace, someone want to jump on this one first?
It's kind of early days at SSC, but we do have a couple programs, one in the SATCOM area and one in the, it's called missile track custody in the surveillance area, that have been, are working at being born digital, kind of like the Sentinel program was for the for the Air Force, and indeed what they've started from day one is requesting that MBSE models that the contractors are developing and taking them through the various milestone reviews, and actually the DMM workshop that the Air Force is hosting tomorrow evening is related to digital reviews and the idea of how, can we change to a culture of doing those versus the very static document-based, reviews that we've always kind of been very familiar with in 5000.2. So I think both those programs, while early days, are actually, walking the talk and doing the action, and they're learning, and there's a lot of lessons learned that have come out from conducting those model-based or digital reviews that we're now sharing across SSC. And so I think that's one example where we're starting to see some successes, and it's more anecdotal because they're early on, but the idea certainly for the missile track custody is they really feel that by doing the model-based approach, they're actually identifying potential later issues that might come up in system integration and test earlier. So it's still ad hoc because you don't have the data to prove that. But I also will mention that through this digital engineering measurement guide that actually Tom and I have been supporting through NDIA. They're putting together metrics and hope to get some data that answers that question about, are we seeing some success there? So we are working on the metrics that would be needed in order to provide the data to show that, yes, we are seeing benefits.
Tom?
Yeah, I think, one area where particularly we've benefited over the years is in concepts like safety and reliability, right? So we're not going to probably see a single engine commercial airliner anytime soon. But 2 inches now is reliable enough. So it's not only those type patterns, but it's the tools, right? So fault trees are patterns and all these kind of things. The OMG's released a new specification called RAML, is the reliability, availability, and assurance modeling language. And so it's tried to take all of these traditional engineering pattern-based tools for doing things like safety and reliability and assurance and collected them together in a standard modeling language. And that's starting to get some uptake. We've used it on our project. So I think we're seeing these initiatives come out to take a lot of these traditional valuable patterns and encode them in models, or in patterns and models, if we want to call them that.
And that's a good example because a lot of that stuff for reliability and safety doesn't happen early enough, and now by having it with the modeling, you actually get to put it even up front with the system models. So that's a really good example, Tom.
Any other comments?
The only thing I was going to say is that I think that to date we've seen more of the kind of application patterns as Marilyn and Tom were talking about. It would be really interesting to ask somebody like John Monley, right, who does this, that's the specific hat that he wears at Northrop. And it's this idea of, I think, the specific question of how do those organizations that have seriously adopted digital engineering and formal model-based engineering, how are they using formal patterns the way that we're starting to talk about it here in their work? I don't know the answer to that question. I wish I knew it, but it's something that we've used. We plot command and control patterns to cyberspace operations patterns. We do this all the time in our engineering work in all domains. I think what's different about this is that we're trying to figure out ways that we can do it more rigorously and in more of a way that allows us to migrate these into our digital engineering our digital engineering ecosystems.
I think this leads into one of the next questions. I'd just like to remind people that there are quite a number of public programs that have been published about pilot projects out of AFRL and other places that have explored this, that are available through INCOSE's MBSE Patterns Working Group website. There's a number of studies in there, many of them aerospace. There's a lot of them outside aerospace as well to go look at. one of the questions, and Bill, I'll ask for you to help address this one, is what's the difference between MBSE patterns or pattern-based MBSE and standards or reference architectures? That's a good question.
Well, we like to, as I started off the session with, just take note of the fact that patterns in general take all kinds of forms. And so formal standards, as Matt's asked about, are a perfectly good example of a pattern in that it's recurrent, it has fixed and variable aspects, and it's things that we've learned the hard way, that we don't want to make a mistake about again, and so forth. In our working group, we're concerned with model-based patterns that go the extra mile of saying, this needs to be a model of a system of some kind. It might be a system that flies around, it might be a system that produces systems that fly around, but it's a model of a system in the sense of what we mean technically by a system. And that's an extra burden on the definition to say, oh, now we're talking about something more than what would go in a standard. So I think, for me, the question that it begs that Matt sort of started out is, at what point can our standards become more oriented in the direction of being configurable models? Because I think we've all benefited from standards, but we've also suffered with the difficulty of stacks of paper and trying to figure out how they affect the project and which part of the standard applies to me and which part does not, and all the issues that go with formalized standards, not to mention just understanding them. And so there's a consistency is a two-way street here, and it says, yes, we would like to have a little more standard basis in our patterns, but we'd also like to have a little more pattern basis in our standards too, I'd say.
Yep. Anybody else want to jump on about standards and government reference architectures? They're a form of a pattern.
Yeah, so I would just note that there's not really any requirement to incorporate patterns into a reference architecture of any type, but you're smart if you do, because they're more knowledgeable, right? So the nice thing about patterns is most of us can recognize them and they match our heuristic knowledge. So if you see one and you're used to using them, then you say, right, I understand this now, right? Instead of the gobbledygook that usually comes down in a reference architecture. The same way, there's no requirement to standardize on a pattern. But it would be nice if some people started doing that in particular ways. And of course they have in some domains. So, I don't know if anybody's done any projects that looked at the relationship between government reference architectures and pattern-based engineering, but that might be something useful to go do.
There is one example of using patterns from SSE. So Dr. Mark McKelvin, who's an aerospace employee, he's developed this model composition pattern framework, and they're actually using it on one of the programs at SSE. And I think to your point, it wasn't that it was mandated to do it, but I think it's really helping them in terms of the consistency and getting people familiar with the stuff. So there is some use there of using this model composition pattern for this program as they're developing the GRA and the system model for it. So.
Yeah. I just want to go back to, based on something you said, Tom, and go back to something that, Bill, you had in one of your introductory slides, right, where you said, patterns are the basis for intelligence, right? They're the basis for how the human brain reasons, right? At some level, we are just pattern recognition and pattern building machines. It becomes so much easier to understand and really understand what you're looking at when you're looking at an architecture or you're looking at a design. If you can begin to recognize those patterns, it allows you to reason about the system in different ways. So the use of patterns, aside from just, this is a sort of a best practice way to do X or best practice way to do Y, it's also a way to communicate the functionality and the structure of your system and your design in a way that becomes much easier for people to consume. It's much easier to talk about, even if the pattern's not perfect, right? It's much easier to talk about, to look at something and say, oh, well, this is the pattern that does X. Oh, but there's this exception. Now I just have to think about this one thing and when it gets invoked. It's so much easier to understand the sentinel concept, right? When you view it as a pattern and understand what it does as a whole versus sort of trying to trace through at the individual component level. It's a different way of reasoning about the system, and it's creating, it's about creating MBSE artifacts that are now closer matches to how, we as dumb humans reason about the stuff that we're doing. And to me, that's really powerful and shouldn't be underestimated.
Yeah, I just wanted to bring up another important aspect of a pattern that is related to another similar term, which is the architecture styles, right? And what I want to get at is basically the idea of patterns establishing some kind of language, taxonomy. Jimmy, you have the example of the taxonomy with the dynamic requirements, right? Mm-hmm. That helps guide the conversation, right? And words, it may seem like, taxonomies are not important, right? But as I think it was Chomsky that said that language is the architecture of thought, right? And that the words that we choose to define things, determine essentially or drive the way that we think about problems, right? So from that perspective, I think, patterns can also be important in choosing the right words, right?
Yep. Well, LLMs are just, they're reasoning on chunks of things, right? They're reasoning about patterns of language. They're not, they're trying to predict patterns of language from chunks of language, not from individual words. So, yeah.
I'll add as a plug for tomorrow's session, it goes into some of the standards and talking about, it's the looking at across 4 different in societies, looking at computational models, where we're going to talk about different standards and how they're not consistent. So if we rely on standards as a form of consistency, you'll get inconsistency between standards. So those are a form of a pattern, but they're not a way to enforce consistency. So we've got to look at how can we look at patterns across all standards here. They're telling us something. So we'll go on to a next question, if somebody else wants to jump in. No? Good. So this one is more geared towards digital engineering, but it asks, what are some of the biggest limitations that modern technology brings to digital engineering? So the biggest limitations modern technology brings to digital engineering. I think we've talked about some of this. Olivia, during the EIC, this has come up a number of times.
Yeah, so obviously there's a cyber aspect, which I'm sure Jimmy will touch on. I think adoption is where kind of, we're trying to, we struggle a little bit, and how do we make sure that we make sure that the technology is not just the technology for the sake of the technology, but that we embed the technology within the processes that we use. So as far as limitation, maybe it comes from most of the human aspect of it, maybe resistance to use of the technology itself, but yeah.
Thank you. Any other limitations for?
Just to throw in on the cyber piece, I do think that's important, but to me it's tied into the workforce challenge, right? So years ago, Richard Danzig wrote a really interesting paper called "Existing on a Diet of Poison Fruit," in which he said, look, these hazards, these cyber risks that we wring our hands about so much, they're all inherent to the reasons we adopted the technology to begin with, right? You want remote access to your data? Well, other people can get remote access to your data. You want cheap commodity computing that can run anything? Well, it's just as happy to run malware as it is to run what you want it to run. And the idea is that you really are in this multi-dimensional risk trade space. And where you are in that trade space is generally not made because of where you should be, but it's made because of considerations of cost or convenience or simplicity or who you ran into at the vendor table at the meeting or whatever it might be. And he said we have to be really deliberate about both how we use technology and what technology we use, because it's what defines where we exist in that space. So to me, while I view the benefits of digital engineering and the revolution that it presents us with an opportunity for, to be a lot like the revolution that information warfare provided, right? Network-centric operations, the way we can transform how we do command and control, because we have this communications technology, networking technology, and information technology. We can now do things that we couldn't even conceive of 20 years ago. But that's a double-edged sword, right? We are now vulnerable to things that we weren't vulnerable to 20 years ago. So I think that we have to think really deliberately about how we use this technology, how we use these approaches, and sort of walk our development along these different axes, very mindful of the impact that it has in all the considerations, not just what the technical limitations are, but what the workforce and cultural limitations are, what the security considerations are, because all those are going to influence the engineering economy that grows out of this.
Jimmy touched on it with the workforce, but I think any modern technology, we know it brings the need for training and upskilling, but I do think what's a little bit different about digital engineering, it's impacting, at least on the acquisition side, for the governments, and impacting across more functional areas. So I think before, when we got a new technology, it impacted the engineering staff, and they had to figure it out. But now we're talking about the logistics, the contracting folks, all the other functional areas, the sustainment, that need to know more about the fact that many of the system designs are being delivered in these models, and they're actually being verified in the models, and the reviews are conducted in these models, right? So I think it's more pervasive in terms of the number of folks that this particular technologies are bringing across the workforce. So I would say that's maybe one difference.
Yeah, great. Go ahead, Tom.
A final plug for technology opportunity, right? So the technology is still pretty new in digital engineering, and the offerings that we're using are coming from many different domains: software, CAD, missions, all these other kind of things. And quite frankly, the price points are from zero to ungodly expensive right now. And so there's a tremendous opportunity for technology disruptors to come in and converge this environment for us. And so, we're starting, our sponsor, Stel, for instance, they're bringing a new offering into the market that's more user-focused and maybe a little cheaper than some other things. And so I think we're not seeing all of the good disruptors yet. I predict we'll see that soon.
But I'd go back to what Bill said. I think we have to think about what is it that we're trying to achieve out of the adoption of these new approaches and new techniques and new technologies, right? Because they're going to affect, how important it's going to be to develop data standards and information exchange standards, and how important is that to how we want to be able to use digital engineering as individual companies, as an industry, as a nation, as a global economy. What we're going to end up being able to do in those areas is going to be determined by how we answer some of those questions. To me, those are the real limitations, right? Is that while it's a Wild West and there's a lot of greenfield of opportunity, that diversity, while it allows for lots of great ideas to grow and emerge and a lot of innovation to take place, how we scale that to be able to use this for collaborative and shared things, how you apply it to systems of systems, how you apply it to broad sections of the industry, it's less clear to me that we understand what the right way forward is there.
Yeah, and I think there is definitely an RI element to it that needs to be accounted for. It's just not necessarily applied across the board, but applied where it makes the most sense. And you may have to make significant investment before you can actually see a return on investment.
That's a key point, right? I mean, those of you who begin to adopt some of these methods, until you sort of get to a critical mass of capability, generating that digital artifact is now just one more extra thing that you have to do. And you're generally doing that in addition to sort of the parallel analog engineering stuff you're doing the old way, right? Until you get to a point where you sort of reach that critical mass or that tipping point, you're still in the negative ROI piece, and a lot of people see it as a cost, which I think contributes to some of the cultural barriers to adopting it, and I mean not unreasonably so. But I think taking the longer view, the sort of question is how do we get over that hump so that we can then get to a point where more and more organizations do start reaching that tipping point, and we really do start to see the cascade of benefit that we think is there.
Bill?
I think the original question kind of reminds us also that in the picture that several of us showed you today, the pattern of the ecosystem as a whole is divided up into three parts. Part of it's about the systems that we engineer that have new emerging technologies in them and all kinds of implications. They're the things that engineers talk about maybe the most. But in the middle, there's a second system called System 2, and it's a gigantic socio-technical system that we're all talking about here, which is how we do that engineering and production and procurement and contracting and all the other things that we do. It's a big, giant system of systems, very complex, but it's a system all the same, and what some of this conversation's about. And then there's a system called System 3 that's interested in governing and representing and designing and evolving System 2. And that formality is a real simple formality, but it helps us sometimes comb out, as several of the speakers have said here, these issues a little bit and say, what are we really talking about here? And think very carefully and deliberately, as Jimmy said.
Mm-hmm. Okay, I would encourage the audience to seek out the sources within AIAA that are exploring this space. The Digital Engineering Integration Committee, committee meetings tonight. Come join us and learn more about this. That of the Systems Engineering Technical Committee. We're expanding out of MBSE and into pattern-based MBSE, so that's a great place to come as well. The Transformative Task Force that's looking at different elements and how they are challenges that one can't solve without the other, but how do you get them working together? And finally, and the home of MBSE patterns is out of INCOSE. And so encourage everybody to at least go view the INCOSE Patterns Working Group website. There's a wealth of information there, more than any other place. And finally, I'd like to thank our distinguished panelists for having a great discussion and providing an overview of how pattern-based MBSE can help with this digital engineering endeavor that everybody's embarking on. So thank you all for joining us. Thank you, panelists, for being up here and talking about this.
And thank you guys for your time.